Okay, so this is a brief review of chapter 3. The main theme of chapter 3 is about orthogonal expansion. So the idea is actually kind of similar to what we learned in Taylor expansion. So remember when in a Taylor expansion, let me use a red pen. In Taylor expansion, we expand a function fx as a Taylor series. So that Taylor series, let me write one term by term, is, let's say at the point A is this fa f prime a 1 x minus a, and then the end derivative at a over n factorial x minus a n power a. So we extend a function using x minus a and these monomials as our basis. And what we talk about in this section is that we try to expand a function using other bases. And then this is a method that was actually introduced by Fourier. Joseph Fourier is a French mathematician in the 18th centuries, and he invented a way to solve a partial differential equation to study heat conductions. And some of his idea is that, okay, let's say if you want to solve this, we are going to come back to this later on in chapter 4. So we want to solve this heat equation with these boundary conditions, and then you can check easily that this is a solution. This is a solution to this problem. Now, what Fourier said is that, okay, if you want to solve this boundary condition with this initial condition, then the solution can be expressed using these as elements. And then you add some coefficients. So these are the bases that you expand this solution into. And if you look at how you determine the coefficients, fx can be written as an infinite series of science functions, and this is what we would call as a Fourier science series, and these an are Fourier coefficients. We are going to learn more about it a little bit later. So you look at this, you said, oh, that's not possible. F is an arbitrary function. How could you express f as a science function, which is a periodic function? The thing is that f, you can expand it from 0 to pi. Say this function is from 0 to pi. You can expand it as an odd periodic function that is from negative pi, and then you keep expanding it, and then it will be a periodic function on the real axis. So that is the basis. Now, the way to determine this is for this to work is because the science function, the sine nx and sine mx, if you do the integration, and we are going to come back to talk about this later on, you will see that this is going to be this integral is going to be 0. How did you find this integral? If you go back to your Calc 2, then you know that the way we find this integral is through this trig identity, sine say A sine B equals to 1/2 of cosine A minus B minus cosine A plus B. So this is a trig identity that we use to prove that this integral here is indeed 0. Now, then once you know this integral, then you can find out these coefficients is given by this formula. These are given by this formula, and these are what we. So in this way, you can express the solution not as a finite function, but as an infinite series. That is the key point of Fourier's method. And then we are going to come back to this later on. So I would like you to do this as a homework problem. Um, Now, in this section 3.2, we expand on the on Fourier's idea in a more abstract setting. As I said, Fourier this is a power series, and in this case, it's a Taylor coefficients. And then a Fourier series is a series that is in this form, and this is for a function that is defined on the interval from negative pi to pi, but we expand this into a periodic function, which actually defined on from negative infinity to positive infinity. And these Fourier coefficients are given by these formulas. So this is an infinite series. Now, when you have an infinite series, first of all, in this example, we just give this function here. This is a step function is the function is 0 here from negative pi to 0, and from 0 to pi is 1, and you just use these formulas here to compute the Fourier coefficient. That's rather straightforward. So this is now this is you look at this function, and then this function is 0 here, and then it is 1 here. You can see that this function actually is from 0 to 1 is actually approximate very well this function, the original function, and this is the wave of this function. Okay, so now we have to look at the norm. We in order to get the abstract theory of Fourier's function, we actually need to introduce a function space, which we call L2AB, is all the functions, integrable functions, so that it's square integrable. So that's square integrable. That we on this function space, we can define what we call as an inner product or dot product. And then you can define the norms, and then this become a function space, and then you can calculate the norm. This example tell you how to calculate the norm of this and the inner product of these two functions and the norm of these functions. And so under this, when you have an inner product, then you can say a function is orthogonal. That means that their inner product is 0. So this that means that these two functions are orthogonal. So therefore, this is just give you an example of showing that all these functions are orthogonal to each other. Again, when you're trying to prove that this kind of formula, you can use the trig identity I just written down. And then also another trig identity that is useful is sin A cosine B equals to 1/2 of sin A plus B minus sin A minus B. Actually, this is plus. Okay, so these are useful formulas when proving this orthogonality. And this is, again, is orthogonal in different interval. In the previous example, it's orthogonal from negative pi to pi. This is orthogonal from 0 to L. So this is just give you another, what we call as a Fourier sine series. Now, when we have an infinite series, you always need to talk about convergence. So when we have let me write an infinite series n from 1 to infinity, we said that this converges to fx. What does it mean? It means that the finite sum of this, which is, I use another index k from 1 to n, fk x, this as a sequence converges to fx. So that is the notion of convergence of infinite series. And now here in the textbook, we talk about three different type of convergence. The first type is point-wise convergence, and then that point-wise convergence just means that this error here defined in this way converges to 0. That's point-wise convergence. And another is mean square convergence. Mean square convergence, you just look at the square of these, the difference, the square of the difference, and then the square of difference goes to 0 is what we call as mean square convergence. And another convergence that we will talk a little bit about is the uniform convergence. Uniform convergence just means that the maximum of these goes to 0 as n goes to capital infinity. So we are not going. These are actually are the kind of material that we learn in analysis 2 or advanced calculus 2. So we are not going to get into detail. So this is just an example showing you that, that these different concept of convergence may be different. Like in this example, you know that this is point-wise convergent to 1 over 1 plus x squared, but it's not uniformly convergent. It's not uniform convergent, but it is mean square convergent. So this is just an example to show you this. And what is next is that why is this theory important? It could be so it tells us that for any L2 function, if this is of a normal system of L2 function, and if this equals to this, then these coefficients are given by these formulas. These coefficients are given by this formula here. So these are what we call as a Fourier coefficients with respect to this orthonormal system. Now this actually is not original Fourier series, so we call it generalized Fourier series, because original Fourier series for this Fn is either sine nx. It's a trigonometry functions or functions like this cosine nx. Okay, so this is just telling you that the best approximation is given by this. This actually is nothing special. It's just that if you have a space here, and then if you have a vector here, and then if you want to find a vector that is here, that on this plane that's close to this, that is just the projection over there. So this is a way to think about this inequality, which we call it best approximation. So this is another example, one of the examples to explain you how to calculate the mass approximation. Now, this uh, you can a system is orthonormal. Here it means that the inner product J, Fj, and Fk is 0 equals to 0 if J not equals to K. That means it's ortho. And then when J equals to K, it equals to 1. So it has norm 1. This is what we call the orthonormal system. Now, your orthonormal system is complete, means that every function f can be expressed as an infinite series of this system. Let's say K from 1 to infinity. So that is the textbook use a different definition, but this is equivalent to this. And this conversion is in L2 in mean square. It's a mean square convergent, and this actually is also equivalent to this Pascal's inequality. Okay, so these are the problems that I would actually like you to think about this problem. Yeah, these problems. And let's see. And this one. Okay, so now we come back to the classical Fourier series, which is the Fourier series that involve the trig functions. So this is the general, what we call is full Fourier series. Full Fourier series. That means that it involves both the sine and the sines and the cosines. So, and in this case, this infinite series and the coefficients are given by these two formulas. And we are going to explain how this formula arrived. And it is all because this is an orthogonal system. And it is a complete orthogonal system for L2 spaces. And then, okay, so this is just a specific example, tell you how to calculate these coefficients. And this actually, the Fourier series actually is the basis of the music theory. And in music theory, like when you have a string of length, say from length L, and when you plug on a string, it will produce a sound, and these sounds are governed by these the quality of these sounds and the timbre of these sounds are actually conveyed on these coefficients, and these are what we call as frequency spectrums, and then Pascal's inequality. Equality is now in this form. So essentially, what you need to know is just to understand these formulas and how did we get this formula and how did we compute the Fourier coefficients using this formula. So this is the definition of the Fourier series, and the coefficient are computed by these two formula, and we will explain how did we arrive for these formulas. And so in this small subsection, you are talking about periodic functions, function you can expand as a periodic functions. And in this example, you are going to ask how to expand this function given by these formulas as a two periodic function. So that means it's a period of 2, and using the Fourier series. And here you just need to compute the coefficients of numerical coefficient of several terms. And then this is also another way of express the Fourier series using the exponential complex exponential functions, and that's we will just touch upon about it. It's not the main thing in this chapter. So unfortunately, because of the time limitation, we will not be able to talk in full detail about the pointwise convergence and the uniform convergence of Fourier series. So, but for this section, the homework problems, let me see, would be this one. And okay, and this one. Let me see. And okay, so yeah, okay, maybe just handing this through. Okay, so I will go over this in detail in the lectures.